Hey Calculus, welcome back. Our objective today is going to be to look at the second part of Fundamental Theorem of Calculus. I've got the checklist on the screen, you know what to do from here. So before we look at Second Fundamental Theorem of Calculus, I do want to do some review of definite integrals and area. I'm going to force a pause on the screen. Can you please see if you can figure out this definite integral given the graph of f of x on the left and these two definite integrals on the right? Okay, we are back. So I got that area B, so all of this area is 7, because area A minus area B should be -5, right? And we have that area A is 2. So I'm getting that again, the area is 7. However, should the integral value be positive or negative? It should be negative because it's all below the x-axis. All right, force another pause on your screen, just your best hunch. See if you can figure out this definite integral for me. Okay, we should have, here is the full integral from 1 to 8 is -5, so we should have -10 here. Just like with derivatives, we can pull out the coefficients to the front. They're just going to come along for the ride. So another way to think of this is 2 times the integral from 1 to 8 of f of x dx. And again, this piece we already knew to be -5, right? So just 2 times -5 will be -10. Think about it graphically as well. When you multiply a number to the outside of a function, it stretches it vertically, right? So all those areas are going to be stretched by a factor of 2. And force another pause on the screen. Your best guess, what do you think the integral from 8 to 1 of f of x dx is? Okay, so for this integral, we should get +5, right? Because when we went forward, we accumulated an integral value of -5. So when we go backwards, we should take the opposite sign, okay? So in this case, we should get +5 because we flipped A and B, okay? So the way we look at this in terms of calculus is that the integral from 8 to 1 of f of x dx is the same as negative integral from 1 to 8 of f of x dx. So we can always flip a and b if we just change the sign in front of the integral. All right, so for this last one, I'm going to force a pause on your screen. I would like for you to just write it down. We'll do it together. Okay, so the real temptation here is to say, oh, the integral from 1 to 8 of f of x was -5, and then just add 3, and the vast majority of the wrong answer is typically -2. You have to be really careful here because look, that +3 is inside the integral, okay? If we say, what most students are calculating is this integral +3, right? Which is not what we have. We're taking the whole function and adding 3, which shifts the whole function up 3, right? So what's going to happen is we create this whole new area. We're going to create a whole nother rectangle, basically underneath what we already had. And so what you want to do when you've got more than one term is remember that you're integrating both pieces, okay? And there's 2 ways to find definite integrals. One is through area under the curve. The other way is through antiderivatives, okay? So let's do this. Write this for me. I'm going to shift up here. Split up the integrals for me. So you've got 2 pieces. You need to integrate both pieces. So we're going to go integral of f of x and the integral of 3. Okay, so I need both pieces. So this part, we already know this is -5, right? Now for the second part, let's use FTC. Let's take an antiderivative and then evaluate at 8 and 1. So an antiderivative for 3 is 3x. I'm going to evaluate that at 8 and 1. Which one should I plug in first? We should plug in 8 first. All right, so I've got, let's zoom in here. I've got -5 plus. Now, when I evaluate at x equals 8, I get 24. Then I need to minus. When I evaluate at x equals 1, I get 3. And notice 24 minus 3 is 21, which is the area of that rectangle, base of 7, height of 3, okay? So Our final answer here should be positive 16. So again, just kind of another graphical explanation as to what we're doing. So I've graphed just good old y equals x squared here, called it g of x, and then I'm going to add c. And remember, when I add c, again, that parabola is going to shift up, right? So what I want you to do is, I'm looking at the area from 0 to 2. I want you to see the area the additional area that's created there as we move the function up by c. See that we are creating this additional rectangle each time, right? So the one we were just doing, we created this additional rectangle underneath with area 21, which is why, like if I were to put C at 3 here, if I were to shift up 3, you can see I didn't just add 3 to the area, right? I added an area of my base of 2 still, and a height of 3. So I actually added an area of 6. So just be really careful that when you have more than one term, that you are considering both terms in the integral. First, to pause on your screen, can you please copy the definite integrals I have for example 2? And then can you draw me a picture of g of x that can satisfy these first two integrals for me? Hit continue when you're ready to check your work. All right, so here is a possibility. I've labeled my areas 3 and 5, but notice I have both of them sitting below the x-axis because both integral values are negative once you have adjusted for your a and your b to be in proper locations, right? Your a value, your smaller value should be on bottom. All right, so now that we've got a decent graph of y equals g of x, I'm going to force another pause on your screen. Can you try the last two integrals, please? All right, we should get -8 and 8 respectively. Go ahead and pause your screen if that's not what you got and make corrections. Force another pause on your screen. Can you please copy both the function f of x as well as the integral, for example 3 here? Okay, so as you can see, we've got a piecewise function now. And what I want to do is find the area from -1 to 1. So if I'm looking at the graph, I would go from here, and this would continue going to here, right? And you can see I have two pieces, correct? So what we're going to do is look at this piece and then add up that area. Okay, so find the two areas individually. And remember, to find area, we can use what? We can use antiderivatives, okay? So here's what we're going to do. Let's grab that first piece, which is valid for x is less than 0. So you can see, where am I going to break up my integral? At x equals 0, right? I could tell from here, or looking at the graph, I can see that's where the two pieces switch. Okay, so here's what we're going to do. Write this for me. We're going to go -1 to 0. Those are all x's less than 0. So that means I'm going to grab the corresponding piece, the -2x dx, right? And then I'm going to add the integral, and I need to pick right back up where I left off, right? Open circle, closed circle, doesn't matter. I need to pick right back up at x equals 0, and then I'm going to finish at x equals 1 here. And those are all x's greater than or equal to 0, so that means I need to use that piece, so e to the x. And now we'll just go ahead and anti-derive and evaluate, okay? And force a pause on the screen. Can you please do these two and add them by hand? All right, we should have gotten E. Okay, we are finally ready for the second fundamental theorem of calculus, which says if f is continuous on an open interval containing x equals a, then for every x in the interval, the derivative of the integral from a to x of f of t dt is equal to f of x. And force pause on your screen. Just go ahead and copy what I've boxed there. Okay, so the proof of this is very straightforward. Let's do this. Let's work with the integral first. I'm going to keep the dx, okay? Now let's work with the stuff in brackets. So if I'm going to evaluate a definite integral, I can find an antiderivative and evaluate it at b and a, correct? So the stuff in brackets would be the same as capital F of b minus capital F of x minus capital F of a. Agreed? Where capital F is an antiderivative for little f. Okay? So now what we're going to do is take the derivative of both terms. Well, if I take the derivative of the antiderivative, That is f of x, right? Well, a is a constant, right? And so f of a is a constant as well. The derivative of a constant is 0. So I do end up getting f of x, which is exactly what we wanted to show. Okay, this is not that surprising. We're basically saying that derivatives and integrals cancel each other out, which we already had this hunch, right? Because integrals are antiderivatives. Okay, so it's saying taking the derivative of an antiderivative takes you back to the original function. Press pause on your screen. Can you please copy the 4 integrals I have? Okay, let's do the first one all the way through, and then let me show you again that this is much easier than having to go derivative, antiderivative. Okay, so first of all, it says capital F of x is defined by that integral. So let's go ahead and find the definite integral, and then it says, okay, now I want you to find capital F prime of x. Okay, so if I'm going to look at just this integral, let's work through this. So I would need an antiderivative, which would be 1/3 t cubed minus 3t, right? And I want to evaluate all of that at x and then 3. That's my b and my a respectively, okay? So when I plug in x, I get 1/3 x cubed minus 3x, right? Just plugging in x for t. And then minus, and now I want to plug in 3, and I'm just going to leave it unsimplified. So 1/3 3 cubed minus 3 times 3. So all of that mess is f of x, right? But it said find f prime of x. So now I need to go take the derivative of all that stuff I just found. Well, isn't that just going to take me back, right? So when I take the derivative, the 3 and the 1/3, that cancels to 1, so I get x squared minus 3, because I'm taking the derivative with respect to x. But notice all the other stuff is just a constant, and the derivative of a constant is 0, so that all goes away. So notice I ended up exactly where I started. The only difference is I switched that t to this letter here, to that variable, the x, okay? That is the only difference. So that's our shortcut. We don't have to do this anti-derive every time. Just replace the inside, or sorry, just replace this variable with that one, and we're good. Now keep in mind, for this first one, it was my b that was the variable. Let's take a look at that second one you wrote. Okay, so here's capital F of x defined as an integral. We want to find f prime. Okay, we know that the derivative and the integral will cancel, so all I need to do is replace this letter with this one. So I'm going to have sine of x, right? With one exception. Do you know what it is? This actually needs to be a negative, because look at our theorem. The x was in the b spot. So if it's not, remember, we can just flip and change the sign. So this will be negative sine of x. All right, let's take a look at that next one. Very similar, okay? The only difference is instead of an x, I've got x squared. So I'm going to start the same way. Replace the t with the x squared. So that's going to give me x squared plus 2. Let's put parentheses around that. Now you just plugged something inside another piece, right? That requires a chain rule. So now multiply by the derivative of the inner part, which is 2x. Okay, so we got a little chain rule inside of second FTC. All right, let's try this one. F of x is defined as an integral. I want to take f prime, right? The derivative of an integral, those will cancel. So I'm just going to replace this letter with that piece. So this is going to be, this should be arrows, not equals. This is going to be cosine of 4x. Now notice that what I just plugged in has its own rate of change, right? So I need chain rule. So derivative of 4x is 4. I'm going to put it in the front here, okay? All right, you all, I'm going to leave you with this last example to bring to class. So find me f prime, capital F prime of x, if capital F is defined by this integral, and we will discuss next time. I'll see you all then.